Well, welcome everybody. Welcome to Geothermal 101. I'm Jay Egg. A little bit about myself, just so you know who's talking. I ended up here in New York almost by accident. John Reiner back there. Raise your hand, John, because I'm going to talk about you just a little bit. John Reiner was with, he lived on Long Island. He's a really, truly nationally renowned hydrogeologist. Has done more geothermal wellbore designs than just about anybody else, the complicated kind, than just about anybody else in the state. And he was with NY-GEO. Now, this is before NY-GEO was actually an organization. And I don't even remember how I ended up at NY-GEO because I live in Florida, and that's where our company is based. But I had just written a couple of books, and I got copies of those up here. I'm not selling them, don't worry. They're available from McGraw-Hill or on Amazon. But I just written a couple of books, so somebody probably invited me up there to talk at NY-GEO, and they had a new law that made it was a regulatory law, if I remember right, John. And you guys had a state senator over there, and they were talking about this, and this was really a new thing, and they were just kicking it off. The next year, they had the first NY-GEO conference, and every single year since then, I have had the privilege of teaching NY-GEO's 101 class. And I've done a lot of other things. There was a couple of years where I taught 2 or 3 8-hour sessions. They actually had me go on a tour of the whole state under a NYSERDA contract to train engineers and architects. So by training, I'm a nuclear power engineer from the U.S. Navy. I got out in the late 80s, started a company, and I actually thought I had invented what you're going to hear about. And in 1990, I found out that it was not the case, that the International Ground Source Heat Pump Association, located in Oklahoma at OSU, had a program on it. So I traveled there in about 1992 and got my certificates on being a geothermal designer. So I took that, added a lot of other things to it. You're going to hear about all the different types of geothermal applications there are out there. Now, just as we get ready to start, I'm just going to ask, by a show of hands, how many people are at a geothermal conference for the first time? Please be proud. Oh my gosh, you're making my heart feel good, because I am going to go easy. We're going to start, like I said, at 2 + 2, and I love doing this because I'm going to try to make the most complicated concepts as simple as a drawing. And by the time you get done, I'm going to do these things right here, and I won't read them to you, but I'll just kind of encapsulate them. I just want for you to leave understanding the context, the verbiage of what we're doing, why it's important, why it's vital, understand the health and human safety applications, the industry goals, the barriers. The number one thing we hear is, why is geothermal not more prevalent? And then give you guys a little bit of empowerment to make these changes wherever you are. And I know that's why you're here. And then go further. There's a lot of things we can do to go further in this technology. This image here is the image where it all started for me with New York, because the New York City Council asked us to come up and present to them how in New York City we would be able to decarbonize with geothermal heat pumps the entire city. And so we began. I had an artist in this drawing, and I'm not saying this for any reason except to give you an idea of where we come from. This drawing cost $15,000. It had a lot of variations and a lot of small things. But I really, really worked our graphic artists, on trying to make something that I would understand as a 10-year-old on what's going on. And guess what? This is from 2015. This is a thermal energy network. This is the concept we were already doing in Florida in resorts and communities and universities and so forth. I was telling somebody else in the last class that we have thousands of these installations in Florida. I cut my teeth there. Now, why don't you hear about that? Why do you think you don't hear about those thousands of installations? Because they're invisible. You can't see them once they're in. And if they make sense, people do them whether they have tax credits or not. And that's one of the arguments. So let me explain what's happening here just briefly, and then we're going to get into the basics. This is just a pipe filled with water, and it is what is defined as the connecting circuit of a thermal energy network. Buildings within a community or a city are either cooling dominant or heating dominant, meaning in the winter you need heating, but what happens in the city, and you're going to hear more about this, some buildings like data centers and office buildings have more heat generated inside than they even need, so they need to exhaust heat. So the thermal energy network concept that you're going to hear about, and we're starting difficult, but we're going to go very easy very quickly, is that cooling dominant spaces reject heat all winter, even on the coldest day. Apartments, single-family homes, and recreational facilities and the like can use that to heat pools, to heat domestic water. And some of the sources and sinks for heating and cooling include wastewater. They include structural piles under buildings. They include surface water. They include even subways. Anywhere water is moving or present is an excellent place. And of course, the earth itself is an amazing heat source and heat sink. So we're talking today about shallow geothermal exchange and how to move it around buildings. Now, in a big picture, there are about 10 different ways and sources and sinks, generally speaking, that you can do it. And we'll come back to this one after we cover some basics. So there are two types of heat pumps that we're going to talk about today: air source heat pumps and ground source heat pumps. An air source heat pump can usually be identified by having some type of a compressor unit outside or hanging on the wall. We're used to seeing the mini units that are shaped kind of like a book and probably about this big. And these air source units, they're efficient. Don't get me wrong. They are very efficient. The problem is, think about in the winter when you're trying to get heat into the space, they run a compressor, and we're going to talk about what that does in a few minutes. They run a compressor and they try to extract heat through compression out of cold outside air. So if an air conditioner is at a certain efficiency rating and it's trying to extract heat from a cold environment, what's going to happen as it gets colder? It's going to use more electricity, and what that does is it reduces its efficiency. Now, what happens, no matter how good of an air source heat pump you have, if it gets cold enough outside, the efficiency goes down to what we call a 1-to-1 ratio. And that means a 1 coefficient of performance. And a 1 coefficient of performance means that if you put 1 kilowatt of energy into a device, you'll get 1 kilowatt of heat out. Now, that's what an electric space heater does. And that's okay as long as the grid can handle it and your electric bill can handle it. But normally, these will run at about a 3 COP. If it's above freezing outside, they'll give you 3 kilowatts of energy for 1 kilowatt of energy consumption, because the 2 kilowatts come from pulling it from outside of the house into this refrigerant stream and then dumping it in the house. Now, the reason a geothermal unit can operate more efficiently is that it's not subjected to the outside air temperatures. The outside air temperatures here, while they might drop well below freezing in the winter, down here in New York, the temperature at 6 feet or below is 55 degrees year-round. So you can extract energy from that ground source year-round, At a high COP, 55 degrees will give a heat pump a COP of about 4.0 to 1. In other words, a 4 COP. It will deliver into the house through ductwork, through radiant floors, through radiators, or creating domestic hot water. It will deliver 4 units of heat for every unit of electricity it uses. And the difference is, instead of an outside condenser, the unit is typically all inside, and the only thing outside is underground and out of sight. So it has benefits there that we're going to talk about. Now, the way it does it is called the Carnot refrigeration cycle. I will not make you go through the steps to fully understand this cycle, but I will tell you your refrigerator has a refrigeration system, and it operates on the same principle, the Carnot refrigeration cycle. And all I want you to do is think about the fact, if your refrigerator's unplugged and you put it into your kitchen, it's going to be the same temperature inside that it is outside of the box. When the compressor system kicks on, it pumps the heat out of the box, and most refrigerators these days usually have the coils down below. And if you think about it, you can remember feeling that heat blow out on your bare feet from time to time. It's pumping heat out of the box, and it's using the Carnot refrigeration cycle to do it so that it can get it well below the ambient temperature. And this is well above your kitchen temperature. That's how it manipulates the heat, because heat only moves from a warmer spot to a colder spot. So it has to manipulate heat concentration, and that's what it does with its 4 components: the compressor, the condenser, the evaporator, and the expansion valve. You don't need to know what they do, except that one's cold, one's hot, and there's a compressor, and it uses electricity. So that's how a refrigerator operates exactly like an air conditioner. An air conditioner is moving heat out of the house to the outside. A refrigerator is moving heat out of the box to outside into your kitchen. And so it uses those 4 components to do it. It's just that a heat pump is normally a split unit. They can be window units too, but these are most common what you see in houses. And it just has the refrigerant lines connecting the different components of the system. And this is the difference when you take that away and replace it with this loop. You take that outside condenser, replace it with the loop that's completely underground. So you really have 3 things happening: fluid in a loop, moving through the ground, and moving that heat into and out of a refrigeration loop, which is the Carnot refrigeration cycle, that can be distributed in the house as either hot air, cold air, hot water, or cold water. And so all the ways that a geothermal heat pump can heat and cool a home are as many as your imagination. Forced air heat, forced air conditioning, radiant heat and air conditioning, radiators, domestic hot water, and even pool heating and spa heating. So just about anything. As a matter of fact, in restaurants, the walk-in coolers, on ships where I came from, all the refrigeration is done by the Carnot, using the Carnot refrigeration cycle. And you'll have copies of these slides when you go home and check your inbox. And if you want to know more about that cycle, you can look at it here on this YouTube video. So the 2 types of distribution that we like to talk about are hydronic, which just means you're using water in a pipe to deliver the energy, or forced air, which means you're forcing air through a duct system like they're doing here. You have registers, and right now it's air conditioning in here, and you can feel that cool air blowing. The very best way to distribute energy, or the most efficient way, is through a pipe, through hydronics. And we won't get a lot into that. This is about as far into the weeds as we'll get, because in the air conditioning field, you will hear a lot about BTUs, and you'll hear a lot about KWs. You'll hear about SEER ratings and COP ratings. This is all I'm going to tell you about it because it's really kind of interesting. We work on the imperial system here in the United States, and we hear a lot about BTUs. A BTU is a British thermal unit. It happens to be the exact amount of energy that one wooden matchstick creates when it is burned from top to bottom. 1 BTU is also the same amount of energy it takes to raise one bottle 1 degree Fahrenheit. So the heat from one matchstick will raise one bottle from 75 degrees to 76 degrees. A watt happens to be equal, and this is the metric to imperial conversion. A watt of electricity is 3.412 BTUs. So if you put 1 watt of electric heat into a bottle, it will give you the equivalent of 3.4 matchsticks worth of energy, or 3.4 BTUs. The energy efficiency rating is used normally in the United States for cooling. The rest of the world uses COP for both cooling and heating. COP is the easiest to understand. EER mixes units, and it's a manufactured rating to complicate things so they're not easily understandable. So I'm not going to talk much about EERs. I'm going to stay with COPs, since most everybody in the heat pump world stays with COPs these days. So COP, I kept mentioning, if you use 1 kilowatt of electricity and get 1 kilowatt of heat into a building, that's a 1 COP. If somehow you are able to give a device 1 kilowatt of electricity and it delivers 2 or 3 times that, 2 or 3 kilowatts more, that means it's a 2.0 or a 3.0 coefficient of performance. So this is where the magic happens. With an electric heater, if you put 1 kilowatt in, you will get 1 kilowatt of heat, which is 3,412 BTUs of heat. If you put 1 kilowatt of electricity into a geothermal heat pump, that 1 kilowatt will run the compressor and the pumps on that heat pump, pick up 4 more units of heat out of the ground, and deliver 5 units of heat into the space, for a grand total of 17,000 BTUs of energy for 1 unit of electricity. And that's how, if you hear constantly that geothermal heat pumps will save the grid, that they levelize energy consumption on the grid, this is why the federal government and the state of New York spend so much time and energy and money implementing these, because I won't get a chance to talk about this in great detail. For every dollar they spend implementing thermal energy networks, like we just heard Jamie Van Nordstrom talk about, for every dollar we spend of the billions of dollars that it's going to take to do it, they will save $3 billion in electrical infrastructure. I'll cover that briefly, but see, it's much smarter to give us electrified technology with geothermal heat pumps, and we'll save a lot of money as a society doing it. So this is what it looks like in an actual installation. If you've ever owned a home or had a home and seen these outside, on the inside, usually hidden, is an air handler, and it's very quiet, and you can hear it moving air through the ductwork into your space. Outside, this is a little bit noisier, and you can hear a slight hum and a little bit of fan noise as it's operating, and that is how an air source heat pump works in practical situations. That happens to be a carrier unit split heat pump there. This is a carrier unitary geothermal heat pump here. They are exactly the same technology. Nothing different, no cost difference, nothing different with the equipment. The only difference is they took the compressor, which is about the size of an oblong basketball, out of here, put it in here, and in place of all these coils out here, these are air-cooled fins, they put what's called a coaxial heat exchanger that's about this big, and it's about that thick, and it's got a hole in the middle, and it mixes the temperature of the refrigerant and the water going down in the ground, just the temperature, through a double wall coaxial exchanger, and that's how it takes the place of the air coil. So all that is now in this bottom section, the compressor, the refrigerant to water exchanger, and so that is now shoved into here, and this is the whole thing. And the first thing people will say is, well, aren't compressors noisy? Well, let me ask you, is your refrigerator noisy? These are no more noisy than a refrigerator. They're built for inside comfort. They meet library classifications for noise. Put that out of your mind. What you hear outside is not what you hear inside with a geothermal heat pump. They're built to be inside. I have challenged people many times on installations when homeowners or business owners say, oh, it's going to be noisy. You open up the thing, put a dB meter by it, and they go, is it on? And it is. They're quiet. So don't worry about it. Think about a refrigerator. And that's how quiet these appliances are. So this is the practical difference. You eliminate the unit outside, and this piece of pipe that's under the ground is what we call permanent infrastructure. Kind of like your septic tank, if you've ever had one. If you put it in the ground and somebody says, well, when will I need to replace this? Well, I hope never. And, it's even more permanent than that because these pipes in the ground are made out of high-density polyethylene, and they have warranties for 50 years, but the Plastic Pipes Institute says they expect it to last 100, even 300 years in the ground. This is just an idea of the wide variation of heat pumps available. Everything from packaged terminal units. Yes, this is a whole heat pump. If you have a house with a bunch of rooms, you can put one of these in each room. And guess what? They're just connected with water pipes, one to another, and connected to your geothermal loop. You can put 5 of these in, like window units, except sit them under the ground and not even use a window. These are what Marriott hotels use. They're called stackable geothermal heat pumps. They've got replaceable components that just slide in like a dresser drawer if you need to put a new fan in or something. These are more commercial units like you'd use in cafeterias, or might even be in a room like this, smaller condo units. The different types of units, the configurations are kind of amazing. You have these vertical water to air. Now, when it says water to air, and this is just how they describe these units, it means you have water from a geothermal loop, and that's transferring energy to an airstream, water to air heat pump. Vertical, because it's vertically oriented. How about this horizontally oriented geothermal heat pump? Where might that go? Oh, in an attic, between the floors in a commercial office building, and it's got the circulators hanging right there, and all they're doing is they're micro amperage circulators, maybe using 0.1 to 0.5 amps, and they're moving water from the loop into the unit and back out, and they operate in conjunction with the unit. You can use water-to-water units for either pool heat pumps or dedicated domestic hot water systems. So if you have a big kitchen in a place like this, you just pick a water-to-water heat pump that's sized for the needs of the whole facility, and you can do it. And it gets better than that. When you're replacing units on Home Depots and Walmarts and schools, rooftop package units, they'll drop right on the curb. So you put in your loop, you pick the rooftop package units. The only difference is they don't have fans on top. They don't need fans anymore. So you can do that. And inside the building for the fresh air needs, you just pick the 100% fresh air unit you need for the fresh air requirements of that building. So now we get to talk about first thing people say, and when we started in business, it was an engineering and construction company. That's what NY-GEO did from 1990 to 2009. And I had a bunch of salesmen, and I said, never talk about ROI, because if you talk about ROI, all people care about is what's my payback. This is, how many times do people go into a Mercedes dealer or a Jaguar dealer or an Audi dealer and say, what's the ROI compared to a Ford Fiesta on this car? What kind of a question is that? You're getting something premium. I say, do not ever get pigeonholed into an ROI conversation. Yes, they pay back, but that's not the selling point of these systems. They are not there for an ROI. They're either there for decarbonization and electrification or as a premium piece of equipment. They will cost more to put in because they have to have infrastructure put in unless there's already a thermal energy network. The ROI works, and that comes as an afterthought. It's like this. Yes, you can put in marble floors and marble countertops and they will last forever. So there is an ROI to that. I don't know how far it would be, but we want to talk about the beauty and the creature comfort. So let's talk about this. No more outdoor equipment to replace. Nothing outside at all. More hurricane and storm resilient for the sustainable communities because there's no equipment to be blown away or destroyed by snow and wind. HVAC system longevity, because it's all indoors like that, they last not 15, not 12 years, but 27 to 30 years average. They increase their lifespan dramatically. And the combustion boilers, cooling towers, and furnaces all go away. You get noticeably superior comfort in both heating and cooling modes because the temperature of the earth is more average, so it can deliver temperatures that are cooler in the summer, remove humidity better, and warmer in the winter. And here's the thing, they don't dry out the air because of flue exhaust and so forth, and they don't wring the moisture out or burn the moisture out of the air. Geothermal heat is very comfortable because of all the above. Remarkable system efficiency at standard equipment pricing. I mentioned to you, and sometimes manufacturers don't like this, but if you go to Carrier or Trane or York and you buy an air source heat pump, they will have a geothermal heat pump of the same quality at about the same price. Yes, you can buy the best heat pump on the market and it's going to cost 3 times more, and it might be worth it. But remember, the builder grade is a builder grade for a reason, because it will last and it will serve you well. And then these thermal energy networks and piping are permanent infrastructure. So as we get into the larger systems, let's talk about, we heard a lot about Framingham, Massachusetts, and I got to go through there. We helped consult a little bit on that at the very beginning. Heat did a marvelous job of making that happen. We were actually casual observers as it went through. And one of the things that was kind of amazing is our company got to help the unions and the activists pass the Utility Thermal Energy Networks and Jobs Act in 2022, which is a whole other story, a really fun story that I like to share, but I won't have time today. But even with that New York passage in February and signing by the governor in July of 2022, Framingham got it done very fast. And that's because they had Eversource and Heat there, a utility and an organization that helped engage the community and make it happen. And that's what we're trying to do here in New York. And there are several on the way. But actually, in West Union, Iowa, Merlin Dunt said, as long as we're tearing up the streets and sidewalks to put in new water mains, we might as well improve the infrastructure at the same time. They actually did the first city-owned thermal energy network of the modern age. The only problem is they missed it on utility engagement. They connected to 60 buildings and still only have 15 hooked up because people don't want to let go of their natural gas. Isn't that something? It is a real problem. It's a real problem with education. I mean, I even listen to my own family. They love those gas stoves. They don't understand induction can work. We're a society that likes fire. We like to see things combust. Isn't it funny? And so we got to get out of that mindset. And we are. This generation coming up is managing that pretty well. So we have to be a little patient. Think about how patient. How many in here were taught the metric system in grade school? Raise your hand. Okay, a few of us. How metric is the United States now? Man, do we move slow. We're the only country, right? So we're slow movers, but we're doing it. All right. By the way, this whole electrification thing, here's a backstory you'll want to remember. I love to share these. The NEMA, the National Electric Manufacturers Association in 1958, was starting to lose ground to, what do you think? Natural gas. So they started this, and that is Ronald Reagan. Yeah, he was a spokesman for NEMA on all electric homes, safer, they won't explode, all the above. They didn't win because during the 50s and 60s, they lost, and we installed 2.5 million miles of natural gas pipeline to 65 million buildings. You could have got one of these medallions, but it didn't. It wasn't enough. And the reason it wasn't enough is because heat pumps weren't there, and we all know there is a great deal of motivation to sell fossil fuels. Finally, we're over that hump, and that's what we're going through now. So I want you to think about that 2.5 million miles of pipe that went into the ground during the 50s and 60s. That is the revolution we are in the midst of now with thermal energy networks. We are doing this in cities throughout the country. John and I have a national view. We're working on projects. He's got a big project in Orlando he's working on. We're working on airports and communities all over the country where entire communities are being dug up. And this is the reason why we're doing it. This test was done in 2010 at the ASHRAE headquarters in Atlanta. They put the very best air source heat pumps in that they could get from the manufacturers on the first floor, and the very best geothermal heat pumps they could get in 2010 on the second floor. Now, a heat pump is a heat pump. Remember that one technology is not better than the other. The only improvements you are going to see are a direct result of the ground temperature and the advantage it has thermally. So during the summertime, the geothermal heat pumps had a 10% improvement on the air source heat pumps. But that's not the story. The story is during the wintertime, you'll notice the first thing I really want you to notice is the peak for the air conditioning in the summertime is not as high as the peak for the heating in the wintertime. What's the number one thing you're going to hear about, or you do hear about now, about electrification? Our grid will not be able to handle full electrification or the heating load we'll have for our buildings. Are the buildings... Now, I understand not all buildings are air conditioned. That aside, if a building is air conditioned now, the peak for the summer will not be is higher than what it will be for the winter, so it will not be a problem. And this has been proven over and over into Ontario, into Canada. So we take what air source heat pumps would do, and this is why the federal government and the state governments are so involved in geothermal, and we take it down to something that the grid and the meter you have on the buildings can handle already. National Grid did a study on this. They liked how it levelized the grid. Oklahoma State did a study of 2 buildings that were installed exactly identical. This is the geothermal line. This is the winter peak line on the identical building with air source heat pumps. Oak Ridge National Laboratories in 2010, that's when a lot of these great reports came out. They proved nationally a 56% reduction in electrical demand just for the summer. And they said an equivalent one for the winter. And they said there would be a 45.3% reduction in carbon emissions. This is a very interesting slide. This was a study done in Ontario. And here is the rubric. They said, they went to Dunsky, which is a very reputable engineering firm. They said, we want to go completely electric in Ontario. Suppose we just put in, now they have 6 or 7 million residents in Ontario, by the way. Suppose we give everybody an air source heat pump. What would that cost and what would that do to our grid? Now check that, and suppose we give everybody in Ontario a geothermal heat pump. What would that do? So you got your two rubrics, right? So one is the teal color is geothermal adoption, and the darker blue color is air source adoption. So the first thing you see here is that they save $1.1 trillion in gas consumption. The installation costs for the geothermal heat pumps are going to be $137 billion more. But their electricity savings very quickly will overcome that, because they will save $137 billion in electricity in the first in the scenario they've laid out here. Here's the important thing. The reduction in infrastructure, in other words, the power lines they won't have to run over the next 30 years, will save them $500 billion. So that's what they see even in the cold climates of Ontario, all the way up through their very cold northern climates. And so this is what, actually there's not a good study of this in the U.S. It's just something that's well understood because of laboratory studies. So they are moving forward with the geothermal. Another thing we don't really want to see is with the the heat pump revolution, is just how messy it can be. And I realize this is a third world country, and so I was kind of showing the contrast here. But these are local boroughs and installations that I'm not sure they were even to code. I would not want to try to work on one of these. So, it's very much an eyesore and not feasible to work on versus all inside equipment. I'm going to spare you the comparisons that the national labs have done on air source versus ground source. It's just that if you look, I'll only say, don't be fooled by the numbers. They use two rubrics for air source efficiency and ground source efficiency. They're not compared by the same measures. The air source efficiency is compared at temperatures that give it a favorable rating because it doesn't get too cold or too hot. The geothermal is constant efficiency. Some DOE data on the efficiency is here if you want to go and research it. It's not important to me because it's obvious that we don't have any reason to think that something that has a warmer source is not going to heat better. It's still an argument some people state, though. So one of the things you're hearing about is laws and codes changing. One of the things our company does is we serve on mechanical code committees, legislative committees. We serve on boards of directors, and we have helped with the trade unions to upgrade the codes. There is actually this code right here for 2021 has geothermal standards for installation. The 2027 code we're working on now will have thermal energy network codes that our unions will use and the utilities will use. These are a couple of the books. We have actually a couple under publication now, one with Elsevier and one for the unions, which will be available through ATP Publishers. Welcome, Jack.
Okay.
Every time Jack walks in the room, I stop. Jack's the only one that's been doing this a little longer than I have in this room for sure. But Jack, thank you for your service. I feel like he's a military veteran that should be saluted. We met him a long time ago, and I still can't believe he's kicking. How old are you, Jack?
Yeah.
Are you really? Holy crap, man. No. Jack, I'm not going to go 19 more years. I'm only 61 this year. I'm not doing that. How do you do that? Oh my gosh. Well, and like you know, my wife is 10 years younger than me, so we married well. Yes. Oh, Jack, it's good to see you. Oh, so we love writing. We write children's books. We do a lot of writing for universities. We've done a lot of writing for the State University of New York. These books you can get on our website. They're free downloads for children. They're activities for middle school and grade school. The other ones you have to buy through Amazon or something like that. We really are into educating the youngsters. We're into educating these types of things. We do free a couple of conferences a month at least. So we're going to talk, and we publish a lot of articles. So if you follow us or anybody, NY-GEO, IGHPA, NY-GEO, we are an information company. We provide, yes, we are a for-profit company. We make profit in spite of ourselves, but we don't work for, we work for cities, states, and governments. So this is our pro bono side. We have a fairly sizable marketing budget, and we spend a lot of time making sure the public is educated. So one of the things we do is we have within our company 3 professional writers, and they write articles at least 3 to 4 a month, and they might appear in ACHR News, PHCP News, Mechanical Hub. If you have this driller, we've been writing for the driller for 15 years. We love Brock Yorty and his beautiful wife, and we support all the publications that are in there. We're equal opportunity. We just put them out there, and whoever wants to publish, somebody always picks it up. What I want to do is this. I love simplicity. So we've talked about natural gas pipelines and how that happened in the 50s and 60s and how thermal energy networks are happening now. If somebody says, you know, I love the guy. I don't understand. What are you doing? I don't understand. This is a great slide to show them. When we put in natural gas networks, we put in a consumptive use chemical gas. It's distributed by a pipe in the ground. It is used, utilization technology, by a furnace or boiler, which combusts it, and it creates heat for hot water or for comfort. With a thermal energy network, we have a pipe in the ground. Same thing. The utilization technology is a piece of equipment that looks no different than a furnace or a boiler. It's a piece of equipment. My battery is running low. Close. I think the thing's still plugged. Yeah, it is still plugged in. It'll be fine. So it's used by a heat pump. And these heat pumps, by the way, you saw the small ones. These heat pumps can fill this room and do a whole city, just like a great big boiler. They can have CO2 refrigerant, ammonia refrigerant, regular, they're the new A2L refrigerants. Anything you can imagine, they operate, and they operate as little as a little teeny heat pump like we saw or something that would do an entire city. And this is the beauty. Just like you saw, there was that one benefit where you eliminate outside equipment. With this system, you get heating and cooling, and the source is not a pipeline that comes from another state. It is the ground you are on, and that's the beautiful thing. This rubric explains exactly what we're doing. So the pipeline routes we have now will be replaced, or they will be added to by these thermal energy networks that go in the ground, and they provide heating and cooling. Now, you're going to see a little bit of that in just a couple of minutes. I'm going to show you a very basic garden variety geothermal installation. So this is a home in Washington, D.C. They needed 3 boreholes. So they got a drill rig in there, just a standard like water well drill rig, and that is how this industry was built, on water well drillers that learned how to do geothermal boreholes. They drilled down about 500 feet, in this case about 250 feet each. They can drill deeper, but that's what they did here. They drilled 3 holes, which were the equivalent of 1 ton of heating and air conditioning each. They connected them together here in a header fashion, and then they buried that loop and connected it to a geothermal heat pump inside the house. And that's it. It's about a week of pain for a lifetime of freedom from anything combustible. This happened to be the sustainability director for the U.S. Navy, and he wanted to prove he could go off the grid, and so he did it with solar and geothermal. We talked about these benefits, so I'm going to move on to another kind of heat pump. It's at the show here. You'll see Total Green Manufacturing. They're very strong in New York and in Ohio. They have this is the system we've been talking about that uses water in the pipes. And it uses, remember I said that refrigerant to water exchanger in the unit? That's a very small part. It's just magnified so you can see it here. Instead of doing that, they take this part out and they said, why don't we take the refrigerant and go out and go into the ground and eliminate this exchanger? What do they get for that? They get a little bit more efficiency. And they have a bulletproof that's been operating for generations system that has a very cool niche in the market. You should check it out. Go by and see Bill Busher. He's a heck of a guy, and he'll show you how to do it. It's this way with a water to air, or this way with what we call direct geothermal. That's under the ground. What are some of the reasons you might do that? Lower footprint. The depth of these is much lower. It's built like a spider. You can see some of those over at their thing. They're completely manufactured. The complete system here is manufactured. And they're kind of cool because if you don't have any room, you can actually saw cut the bottom of your garage out or something like that and install it right in your garage and put a cover plate over it. There are all kinds of ways you can do this. It's a much smaller footprint. They use a little teeny drill rig that looks like this. This is a guy's drill rig out of West New York here, and very small footprint, and that's all you see outside, and that's what it looks like. So check them out. They're here. They're a huge sponsor of the conference, and I love those guys because I've toured them. I don't get behind anything very easily. As a matter of fact, I've covered these in both of our books here. In my first book, I said, what if the refrigerant leaks? And then I found out, yeah, so what? It evaporates. Look at the MSDS. And they give a guarantee that it won't leak, and they stand behind their warranty. So yes, copper is more likely to fail than HDPE, but it's not something we should be concerned about. Do you think we're going to go right to questions, or do we need to get it? Okay. Oh, it's kind of coming back on. Yeah, it went dead. That's okay. You know, the time is 9 minutes till the top of the hour. The only thing you are going to see more than what I just shared, and you'll get the slides after the conference, is a bunch of big projects we're working on. One of the projects we're working on, just to give you an idea of where this can go with these thermal energy networks, we're working on the Amalgamated Housing Cooperative in the Bronx, and they're using a technology that I was going to share a slide on called wastewater energy transfer. So they have a special thing in a box called a piranha. And this piranha, it's about the size of one of these tables and about yay high. They intercept, and these are 222-story apartment buildings. They intercept the wastewater before it goes to the city. And now I want you to think about something. Don't think about anything gross. Just think about what I'm going to tell you. Every bit of wastewater that comes out of that building, no matter how cold or hot it is outside, is 65 to 75 degrees year-round. So where does that heat come from when the water coming in the winter is just barely above 40 degrees? It comes from water heating, it comes from cooking, it comes from showering, and it comes from the heating of the building. It's just absorbed. So what that is, and you'll see it if you Google it in the Wall Street Journal about wastewater energy transfer, they had an article come out just yesterday that talked about what a revolution this is. Because for buildings that are burnt, that are combusting fossil fuels, this shark or wet wastewater energy transfer technology will offset all of their water heating needs for the building normally, and much of their space heating needs, and it will also help their cooling needs, because in the summer when it's 100 degrees outside, that wastewater stream is still 65 to 75 degrees, so they can actually inject heat from the building into the wastewater, and it carries it out. Now, it sounds a little complex. All you need to know is that there's a magic box called a piranha that does it, and it does a lot of nasty stuff we don't want to talk about, but it handles it very well. It's just kind of like, who wants to know water treatment? Who wants to know, anything about where it goes? That's all I can say. And so they handle it. They handled an untouchable subject, and they did it well. So actually, we won a nice CERTA prize for this concept, because we said, why drill holes? Let's do wastewater energy transfer. And the Empire Building Challenge for New York State awarded us and another engineer an amalgamated $3 million to complete the project. So the Wall Street Journal just wrote it up a little bit. They're doing a 3-part series. You need to hear tomorrow. Aaron with Shark will be talking at 12:45 in room 1, and you can hear all about wastewater energy transfer. We work very closely with these guys, and we have for about 15 years, and it's an amazing technology. We do a lot of these large projects, and now I am just going to turn it over to Matt for any questions, because we still have about 6 minutes.
So I wasn't able to go to the morning session, but I think you got some instruction that says when I give you this microphone, you say your name and where you're from, and then you ask your question. And it should be a question. So who wants to start?
What were your instructions? Tony Elba Pratt. Good morning. So we're in New York City. The refrigerant problem to me is very problematic, because between the global warming potential of the refrigerants, the change in the refrigerant and the heat pumps and the fire department. So do you have a simple solution, or what I mean, just trying to buy a heat pump chiller that will meet, it's been frustrating me particularly.
Okay, for a simple solution on heat pumps, I was actually the chairman of the A2L committee for the International Association of Plumbing and Mechanical Officials, and that it was a contentious, very hard thing, because I'm with you on that. There are 2 refrigerants that you can buy that don't have global warming potential. One you can't use in residential because it's ammonia, and it's used for ice plants and central energy plants. And 2 is the CO2 refrigerants. They're becoming more and more available. As a matter of fact, here at the show, you will see, think of the word oil-on, look for an oil-on heat pump. They are here, and they use CO2 in their heat pumps, and they can create steam to replace steam boilers. So it's on the way. Better than that, though, I'm not telling you to wait it out. Solid state technology for heat pumps is on the way, where they're able to do it without any moving parts. It, by all accounts, it's going to be 2035, about 10 years before it's feasible commercially. But we will soon have, you're probably familiar with, you can buy a little refrigerator for your car that has no moving parts. It uses a thermocouple technology, but it doesn't have very high efficiency. It's something similar to that that's coming together. So soon there will be no refrigerants, but for right now, just use the lowest global warming potential refrigerant that you can get. And if you can't get CO2, you're going to be stuck with the R32A, which is the new one.
But thank you.
You're welcome.
But
Thank you, Hendricks with Wilden Energy Solutions. Mr. Egg, air versus ground, first cost versus long-term benefits. How do you deal with that?
That is the ROI question. And I can tell you this is a simple ratio that anybody in the industry that's been here for a while can agree with. Let's just say an air source system costs $10,000. To do the ground source portion, you have 2.5 the cost. So in other words, if it's $10,000, it's going to be $25,000 to do a geothermal. So that's usually the cost increase. The federal government gives 30% through the IRA right now, and that's been the case for almost since 2009. But there are local benefits that provide $5,000 through your local utility. So you can't quite get to zero, but you can get very close with current incentives. So yeah, that's about the cost. And I always equate it to this. Before we had running water in our homes and buildings, if you wanted to outfit a house with water, you had to go out and drill a water well, right? That's the expense. It's the one-time expense you have to do so that you have running water. This is the one-time expense you need to do if you want to have a geothermal heat pump. So you got to look at it like that. However, with the way thermal energy networks are coming along, I can't say how fast. I think it's going to be 30 years of proper build out to match the natural gas infrastructure build out. But we've been privileged. I would be remiss if I didn't share this. There's a little hamlet called Speedsville, which is a hamlet off of the town of Caroline, the village of Caroline, to the west of here. And they are funded. We're doing a study for them. We're in about the third year. They don't even have any infrastructure in their ground at all. They don't even have running water to any of their buildings. So they did a study with NYSERDA that we just completed to do an energy network in their town square because they have enough buildings around it. And we think they're going to do it. Now, why would we do that? Sorry, I'm going to ramble one more moment because I think it matters. The average home in that hamlet of Speedsville in the summer, Bill, is that you? Huh, you have short hair. Do you have it back here? Did you cut it all off? Wow, you look great. You look like one of my scientists, actually. It took me a second. We're over? I'm sorry. So what I'm going to just say is we're fixing energy poverty there because they're spending about $800 a month on propane now. And with the geothermal heat pumps, it will cost about $125 to $150 a month. And so energy poverty is a big thing. Thank you, everybody. I could go all day, but I don't want to. Thanks.